thanks. It's a pleasure to be here. Great, so what? Okay, great. So one question you might ask is, low-dimensional topologists, so I study, three manifolds and knots inside of them. So you might ask, well, how can we construct new three manifolds? So all of our three manifolds today are going to be closed and oriented. Okay. And so, well, one way we can construct new three manifolds is via something called knot surgery. So let me tell you what this is. So let K be a knot in the three sphere. So that's just a smoothly embedded S1. Okay. So how are we going to make a new three manifold? Well, one thing is we could remove a neighborhood of K from S3. So let's thicken this up. Okay. So if I remove a neighborhood of this knot from S3, what I'm left with is the knot complement. That's something with a torus boundary. Well, we want to get a closed three manifold. So now, well, if I remove a neighborhood of this knot, I removed a solid torus from S3. And now, well, let's glue that back in, but a different way. So take S3 minus a neighborhood of K, and then attach to that a solid torus. But you want to do that in a different way than you took it out. So what is one way to do that? Well, so I'm going to glue in. So the idea is, I took out the knot, and I want to fill back in what I took out in a different way. And so I'm going to tell you how to fill that in. I'm going to pick a circle on the boundary, right? So the boundary is a torus. I'm going to pick a circle on that boundary, and then I'm going to glue a disk whose boundary is that circle. And then after you do that, well, right, if you have a torus and you glue in a disk along some essential simple closed curve, well, the boundary of what's left is going to be S2, and so you can just fill that in with a 2-ball. So the point is that to specify how I want to glue this solid torus in, it's enough to specify a curve on the boundary. So for example, here's a curve on the boundary. And so, well, on a knot complement, right, the boundary is a torus, and if you can and there's sort of two distinguished curves on that boundary. So one is the longitude that sort of runs parallel to the knot, and the other is the meridian that just sort of goes around one this way. So the curve that I've drawn here goes around the meridian twice and the longitude once. And so if we glue a disk along this curve and then glue a 3-ball in what's remaining, that's what's called P over Q surgery on K. Okay. And so we'd also just denote this by just drawing the knot and then putting the surgery coefficient next to it. So this means do P over Q surgery along this knot. And I guess P and Q should be relatively prime, so that this is a simple closed curve. And then we denote the resulting manifold. This is P over Q surgery along K. Okay. Questions about this operation of making a new three manifold? Okay. Great. So so now that I've described what surgery along a knot is, well, you might wonder, can every three-manifold be obtained this way? Okay, great. So, well, so, you know, talking about manifolds, we have lots of different invariants of manifolds. So one that you probably all saw in graduate school is first homology. So if you want to compute the first homology of surgery along K, well, right, so surgery along K is described as, well, we had this knot complement, we had this solid torus, and we were gluing them together. And so remember, when you learned about homology in graduate school, well, you had a way of computing the homology of a space that was constructed by gluing together some pieces, right? So you can use the Meyer-Vietoris sequence. Right, so you should let, well, one of your pieces should be your knot complement. Your other piece should be a solid torus. I guess technically, to use Meyer-Vietoris, we should take like neighborhoods of all these things, but that's not going to change anything. So then the intersection is going to be a torus, right? It's going to be sort of the boundary of this neighborhood of your knot, and their union is surgery along your knot. Okay. And so the relevant portion of the Meyer-Vietoris sequence is going to be H1 of their intersection goes to H1 of A plus H1 of B goes to H1 of their union. This, you can look at relative Meyer-Vietoris. You can see this is going to go to 0. So H1 of the torus is Z squared. H1 of the knot complement, it's not so hard to see that this is going to be Z. H1 of a solid torus is also Z. Great. And now, if you think about it carefully for a minute, you can show that this map here can be represented by the matrix P something 0, 1. And so in particular, well, this shows that this is going to be Z mod PC. OK, so the upshot is that the first homology of surgery along a knot is cyclic. So already, well, this is providing obstructions. You know, so well, there are three manifolds that don't have cyclic H1. So for example, H1 of RP3 connects some RP3 is Z mod 2 plus Z mod 2, so not cyclic. H1 of the 3 torus, so S1 cross S1 cross S1, well, this is Z cubed, also not cyclic. So, you know, there's lots of other examples, but so the answer to this question is no. Okay. But, well, you know, this might lead you to wonder, is there some construction that we can do that produces, you know, any closed-oriented three-manifold? And the answer is yes. So the following theorem due to Licorice and Wallace from the 60s. So it says that every closed-oriented three-manifold can be obtained as surgery on a link. Right? So the point is, you might need to have many different S1s embedded in an S3, and then for each of those copies of S1, you remove a neighborhood of it and glue back in a solid torus in some different way. And if you allow yourself to have multiple components, well, then you can construct any three-manifold that way. So for example, both of these are surgery on a link, right? So RP3, well, that's surgery. You can obtain that by surgery on the unknot. That's just take the unknot and do 2 surgery on it. And so if you want the connected sum, well, you can just do surgery on the 2-component unlink. And this one, you can obtain this as surgery on the Borromean rings. So the Borromean rings are the following link. Hold on. Sorry. I want to make this alternating, so this should be an over. Sorry. Okay.
Just drag and fix the crossing.
Yeah, okay. So, okay. Wait, so this, and imagine that it should be it should be alternating. So if this is an overcrossing like this, then this should be an undercrossing like this. Okay, good. Now it looks right. Okay, terrific. And then 0 surgery on each component. Okay. Excellent. Okay. Good. Okay. So we showed that, so I've told you that every 3-manifold can be attained at surgery on a link. So now maybe the question we want to ask ourselves is, which 3-manifolds can we get by surgery on a knot? Okay, so we've already used homology as an obstruction. Well, what other invariants of spaces do we have? Well, we have the fundamental group. So you might wonder, can you use the fundamental group to obstruct something from being surgery on a knot? And so, well, the answer is going to be yes. So let me tell you how you might do that. So, okay, so well, how? So if you want to compute pi1 of surgery on a knot, well, that's you can use Seifert-Van Kampen, and so pi1 of surgery along a knot is going to be a quotient of pi1 of the knot complement. So maybe as a first step, we want to understand the fundamental group of a knot complement. So, so here is a knot. We remove a neighborhood of that. And so it turns out that the fundamental group of a knot complement is normally generated by meridian. So what do I mean by that? So if you look at this diagram and you want to compute the fundamental group, well, take your base point to be out here, and well, you could choose as generators. So in this diagram, we see these 3 different arcs. And so if you just choose a loop for each of those arcs, it sort of goes around like this. So there's one, here's another, and here's a third. Right. those three loops are going to generate the fundamental group for the complement. And then you can check that actually these, like this loop is the conjugate of this one, right? If you could imagine you sort of go over to this crossing and you sort of you conjugate by the loop that goes around this crossing. And so you can show that these three curves generate the fundamental group of the complement, and they're all conjugate to each other. And so if you have a group that's normally generated by a single element, that group is called weight 1. OK. So the fundamental group of the knot complement is normally generated by a single element. And the fundamental group of surgery along a knot is a quotient of this. So in particular, the fundamental group of surgery is also weight 1. OK. And in fact, right, so we've seen that the fundamental group of surgery in a knot has to be weight 1. And you can view this as a generalization of the homological obstruction, right? Because H1 is just the abelianization of pi 1. And the abelianization of, well, if you have a group that's normally generated by a single element, its abelianization better be cyclic. All right. So let me give you an example of what this can obstruct. So you could consider let's say the connected sum of 3 lens spaces, say LP1, LQ1, and LR1, where P, Q, and R are relatively prime. Well, pi 1 of this is going to be just the free product of Z mod P, Z mod Q, and Z mod R. And H1 is cyclic, since these are relatively prime. But Howie showed that this group is not weight 1. So this connected sum of 3 lens spaces can't be surgery on a knot in S3. So for people who don't think about surgery very much, one remark to make about this is you might say, well, can you ever get connected sums as surgery on a knot in S3? And you can. So just as a remark. So for example, if you do 6 surgery along the trefoil, this is actually L31 connects sum L21. So you can get connected sums of 2 lens spaces as surgery on a knot in S3. But you can't get this connected sum of 3 different lens spaces as surgery as a knot in S3. Any questions?
What's the best known bound and the number of connected summands, like from work on the Heegaard conjecture?
Oh, so there's the 3 summands conjecture, which is
you can't get more than 3 summands.
That's right. And I guess the conjecture is that you can only get 2, and that they'd be the ones from the conjecture. Okay. So what else is known about manifolds that are not surgery on a knot? So a result of Boyer and Lines from 1990, they gave infinitely many prime Seifert-Fradberg manifolds So if you don't know what a cipher-fibered manifold is, it's a manifold that you can write as a union of circles in sort of an especially nice way. Right, so they give infinitely many prime cipher-fibered manifolds. So with weight 1 fundamental group, so the fundamental group obstruction vanishes. And then these are not surgery on a knot. Okay, and so their obstruction relied on the linking form. So in particular, their obstruction required non-trivial H. Okay. So in light of their examples, you might say, OK, well, since their obstruction required non-trivial H1, well, what can we say about integer homology spheres, spaces that have trivial H1? So, are there integer homology spheres? So these are 3 manifolds of the same integer homology as S3, which cannot be realized as surgery on a knot. Okay. So there's a result of Gordon and Lukey from 89 that says that, well, if surgery on a knot gives you a connected sum, so if it's, or let's say each of these yi's is prime, well then one of the yi had to be a non-trivial length space. So in particular, if you get something that's reducible, well, it had to have non-trivial first homology. So in particular, a reducible integer homology sphere can't be surgery on a knot. So reducible integer homology sphere, it cannot be surgery. Okay. So well then, let's just change our question. So then, are there irreducible integer homology spheres that cannot, which cannot be realized as surgery on a knot? Okay. And so in the late 90s, Dave Ockley answered this question in the affirmative. So he constructed 2 examples of integer homology spheres that he showed were not surgery on a knot. One was toroidal, and one was hyperbolic. His proof relied on gauge theory. And so for a long time, those are the only 2 examples that were known. So now we've come to the theorem that I want to tell you about. So for even p at least 8, let yp be the Seifert-Freiberg integer homology sphere sigma 2p minus 1, 2p plus 1. So maybe as an aside for, if you're wondering what this space is, so in general, if you want to take sigma pqr, where pq and r are relatively prime, this is the link of the singularity x to the p plus y to the q plus z to the r equals 0. Anyway, so that's what these spaces. That's one way to think of these spaces. Then, OK, so the first part is, well, these are not surgery on a knot. Do I want p? Oh, yes. Yes. Thanks. Great. Now it's the correct statement. Great. OK, then yp is. Yeah, p is that. Yeah, it's even, so it's an integer. Yeah, great. That was the question. OK, so yp is not surgery on a knot. OK, well, then you might say, well, how many components do you need to do surgery on to get this? Well, it turns out you only need 2 components. So yp is surgery on a 2-component link. You might also ask, well, could you have used the fundamental group to obstruct these things from being surgery on a knot in S3? So the answer is no. Its fundamental group has weight 1. And then you might also ask yourself, well, how different are these examples? Are they different from Ockley's examples? And they're different in sort of a strong sense. So no yp is rationally homology cobordant to each other, nor to Ockley's examples. So for the non-topologists in the audience, just take this to mean, they're not only like they're different, and they're like really different, and they're really different from those examples too.
What's the significance of homology cobordism for these examples?
Oh, so his are actually, they're both, his examples are, by his construction, they're homology cobordant to S3. And none of these are.
Okay. So is the base and the Seifert vibration here different from the ones in the Boyer lines examples?
I don't know.
Yeah, I think they have different
Is it different?
They have different base code.
OK.
Those all come from drilling out of fiber and concrete.
So that's the theorem. And then, so about 15 minutes before this talk, Alan came out and found Ty and I and answered Ty's question from lunch on Friday in the affirmative. Great, so 45 minutes ago, Alan sent an email to Ty and I that I briefly looked at that seems to do what we want it to do. And so assuming it does what we want it to, you can upgrade this. You can upgrade this, and we can actually construct infinitely many hyperbolic integer homology spheres, which are not surgery on a knot. What's the relationship between these guys and these guys? So the
Are they
wait. So we. Oh.
Are they surgeries on a knot in the
That's right. Yeah. So these are actually these are so take some large connect sum of point Poincare homology spheres. So what the paper that Alan sent to us said that you can always find a genus 1 hyperbolic knot in any three-manifold. So then we do surgery on a genus 1 hyperbolic knot in a large connect sum of Poincare homology spheres. Okay, so that's the exciting upgrade to the theorem. Questions?
The positive result, like iteration, which say, I mean, this problem seems to have no natural answer, right? Question.
Oh, I guess.
Three manifolds that are achieved this way is.
Yeah, so the answer seems. I mean, sort of this evidence seems to be, there's lots that are not achieved this way.
Positive result.
Oh, which are the three manifolds you can get?
Three manifolds are achieved then.
None of which line spaces, for instance, come from alternate methods of surgery. You would change the P over Q conditions and modify all the lens spaces that come this way. You can get all the lens spaces by P over Q surgery on the other side.
If you look at certain classes of three manifolds, you can get a positive answer, but it seems it's hard. Yeah, it's hard in general.
I mean, positive doesn't make sense because all the examples that everyone is taught, their surgeries are not suggested. So this is the natural question I ask: what can be done? All the surgeries on the truck, all the surgeries on the figure eight, all the examples that people are used to, those are all surgeries on lots of theory. So this is asking what is not a surgery on lots
The answer is, I'm trying to understand where this question is going. It seems licorice answered the question cleanly.
Yeah.
That's right.
So you learn nothing about a manifold if I tell you it's obtained as a surgery on all those things.
Okay.
Because they're all obtained as surgeries on those things.
Maybe a more relevant point is that we don't have a good way to describe a lot of manifolds besides being surgeries on something. So somehow your question is asking for a positive answer and giving an alternative description, which we often don't have access to.
It reminds me a bit of this problem carrying the shape of a drum, which is highly false. And then people make more and more counterexamples and more examples with side conditions. And the question is where we're going with the problem. So that's
So if I have time at the end, I'll sort of maybe address a little bit your question. Other questions? Okay. Great. So we have this theorem. You might wonder, well, okay, so what sort of tools do we use to prove this theorem? And so the proof relies on Heegaard Floer homology. So this is a package of three-manifold invariants due to Ozsvath and Szabo. Okay. So Heegaard Floer homology, well, to a three-manifold, we associate some algebraic object. That algebraic object is going to be a module over a ring. So to a closed three-manifold Y, we associate something called HF plus of Y. So this is a graded F adjoin U module where F is going to be the field of two elements. U is a formal variable. This is a graded F adjoin U module, so let me tell you the degree of U. The degree of U is -2. Great. So we'll just take, for this talk, we'll just take Heegaard Floer homology to just be this black box. So to a three-manifold, we associate this module. Let me give you some examples. So the Heegaard Floer homology HF plus of the 3-sphere looks like F adjoin U inverse, then modded out by U times F adjoin U. Right, so this is, and it's, all right, so I have a U inverse in here, but this is an F adjoin U module, so I have this U action on here. So just to be more compact, I might write this as F adjoin U inverse. Right, so where so 1 sits in here, and then U times 1, well, that's in here, so that's 0. And this is a graded F adjoin U module. So let me tell you since we know that U has degree -2, if I just tell you the grading of one element in here, that'll determine the grading everywhere. So I'll write that like this. And so this will just denote, this notation will denote that the grading of 1 is 0. Right, and then that determines the grading of everything, right? So U inverse is going to have grading 2, etc. Maybe a couple other examples. So the Heegaard Floer homology of, if I do +1 surgery on the trefoil, it looks a lot like the Heegaard Floer homology for S3, except the grading is different. Now 1 sits in grading -2. Let me give you a more interesting example. So let's look at the Heegaard Floer homology for +1 surgery on the torus knot T215. So the trefoil is a torus knot T23. So here's a slightly more complicated knot. And then its Heegaard Floer homology looks like F adjoin U inverse, and then 1 is in grading -8. F adjoin U mod U cubed. I'll say in a minute what I mean by this grading notation. Great, so that's the Heegaard Floer homology for +1 surgery on T215. And so for all these summands, the subscript always denotes the grading of 1 sitting in here, right? So in this, in here, this denotes the grading of 1. All right. Great, so now we have some examples. All right, so you might wonder, okay, well, for these different examples, the Heegaard Floer homology looked really different. What are some features that you always see? So today we'll mostly care about integer homology spheres, so we'll focus on that case. So if you have an integer homology sphere, well, its Heegaard Floer homology can always be written as there's one piece that's F adjoin U inverse, and then there's the rest is sort of this finitely generated stuff. So then you see a bunch of summands that look like F adjoin U mod U to some power. So that's the form that HF plus always takes. This thing is a canonical submodule, right? So what is this stuff, right? So we have this U action, and you say, okay, well, I can act by U, what's all the stuff that's in HF plus that's in the image of U for arbitrarily high powers of U? Right? If you just pick U bigger than any of these ni's, well, if you act by that many powers of U, you're going to kill off all this part. So this F adjoint U part is this canonical submodule, just all the stuff that's in the image of arbitrarily high powers of U. And so then you can look in this summon, you can look for the lowest graded piece of that, right? You just say, okay, well, look at this submodule. Yeah, it's a canonical submodule. Look at the submodule, look for the lowest graded piece in that. And that's what's called the D invariant. So this is the grading of 1, where you look at the one that's sort of sitting in this F adjoined U inverse piece. And Ozsvath and Szabo showed that the D invariant, well, this is an invariant of spin C rational homology cobordism. Okay. Questions? Okay. So how do we use this to provide an obstruction to being surgery on a knot in the 3-sphere? So we have the following theorem. So which says that, well, if an integer homology sphere Y is surgery on a knot in S3, and D of Y is less than or equal to -8, well then, so let's give this part of HF plus a name. We'll use the same name that everyone else calls it, which is HF red. Red stands for reduced. Okay. So if you have an integer homology sphere that's surgery on a knot in S3 and D is less than or equal to -8, then if you act with U on the part of HF red that's in grading 0, this is non-zero. Okay. So this gives an obstruction to an integer homology sphere being surgery on a knot in S3. Let's just check that, well, the obstruction better fail on this example, right? Because this manifold is surgery on a knot in S3. D is the grading of 1 in here, so D is -8, so it satisfies the hypothesis. So there better be some there better be some element in HF red in grading 0 that when we act on it by U, we get something non-zero. So I guess it's time for a quiz. Can someone tell me where that element in there lives? Jeremy?
The second term, is that right?
Second, going from, which is the first? This is?
The -8 tower.
This is the first?
That's my guess.
And this is the second. So this looks like 1 U and U squared, right? And then the 1 is sitting in grading -2. U lowers grading by 2, right? So here you have 1 U and U squared. This is in grading -2. U lowers grading by 2, so this is in grading -4. This is in grading. Yeah. So the grading always denotes the grading of 1 sitting. So it's sort of, yeah, it's a little confusing because the notation for this and this is sort of like different. But the point is, right, for all of these, you look at 1 sitting in this, and the subscript is the grading of 1. So Jeremy failed. Is that going to make everyone else shy? Any other takers?
Doesn't it have to be the one right next to it?
Doesn't it have to be the one right next to it? Yeah, so So the subscript denotes the grading of 1. So 1 sitting in here is in grading 0, right? And well, this again, okay, we can multiply by u, we can multiply by u squared. Once you multiply by u cubed, then we're quotienting out. So yeah, so u times 1 is u, and that's non-zero in here. Exactly. So the 1 sitting in here, when you act on it by u, it's non-zero, and so it's exactly in here where we get something in HF red and grading 0 that u acts non-trivially on. Great. Good work. You all pass. All right. Good. All right. So that's the obstruction. And so then I guess the other ingredient for the theorem would be to show that we can use this obstruction to apply to the YPs that were in the theorem. So theorem 3. Let p be a positive even integer. And yp as above. Then, so the first should tell you something about the D invariant of these things. D is negative p. And then the second thing, well, it's exactly that u acts trivially on the 0 graded piece of HF red. Good. Okay. Questions? All right. So now, let me just prove all the parts of the theorem. Okay, so, well, the first part of the theorem, that was the result that said that these YP are not surgery on a knot in S3. Well, now this just follows from theorems 2 and 3. Great. The second statement in the theorem was that these manifolds were surgery on a 2-component link. And so, in fact, I can just give you the explicit description. So here I want p full twists. And then if you do negative p minus 1 surgery on one component and negative p plus 1 surgery on the other component, that gives us our manifolds. The third statement in the theorem was that the fundamental group was weight 1. So let me give you a presentation for the fundamental group of this space. So pi 1 of yp, you can write with 4 generators. So H is central. X to the p is h to the a, just for some a. Y to the p, 2p minus 1 is h to the b. Z to the 2p plus 1 is h to the c. And h to the e times x, y, z is 1. OK, so I just want to show that this fundamental group has weight 1. So I just want to show that it's normally generated by a single element. So the claim is that this group is normally generated by h to the e xy. So how are you going to show that? Well, let's just quotient by the normal closure of this and show that we get the trivial group. So let's consider pi1 of yp quotiented by the normal subgroup generated by h to the e xy. Okay. So we don't need z. Wait. So z is trivial now, right? In this quotient. So we can get rid of z. So now just h to the c is 1, and, well, h to the e xy is 1. OK, and now we can ditch y. You can ditch y as a generator, right? Y is equal to h to the e times x inverse. So ditch y. OK. But, OK, so now if you look at this, I have two generators and one of them is central. So in particular, this group is abelian. So what else do we know? Well, yp was an integer homology sphere. So yp was an integer homology sphere. That means that h1 is trivial. Remember, h1 is the abelianization of pi1. So if the abelianization of this is trivial, well, then any abelian quotient better be trivial. So this one, pi1 of yp abelianizes to h1 of yp, which is 0. So this tells us that that tells us what we want. That tells us that this quotient better have been 0. Great. Okay. So that was the third part of the theorem. And then the fourth part of the theorem was just that these examples were not homology cobordant to each other, nor to Ockley's examples. So, well, the D invariant of y sub p is negative p, and the D invariant is an invariant of rational homology cobordism. So they're not homology cobordant to each other, and the D invariant of Ockley's example was 0. Wait, so that does it. So that's the proof of the theorem. And so I'll conclude with maybe some further questions. Right, so, OK, so Licorice and Wallace tell us that every closed three manifold can be written as surgery on a link. Our result shows that, well, for many examples, you need at least two components. OK, so you can define something called the surgery number. So let the surgery number, this is going to be the minimum number of components needed to write y as surgery on a link. And so if you're doing surgery on a link, well, then your surgery coefficients is going to be some vector, right? Some some number, a rational number for each component. Actually, so let's first, so from a topological point of view, it's natural, if your surgery coefficients are integral, that's sort of special and nice. So you could ask, well, what's the minimum number of components you need to write your y as an integral surgery? So each of these is an integer. Or you might loosen it and allow rational coefficients, and then let's call that the Dane surgery number, S sub d. So this is the same thing, but now we allow rational coefficients. And so then, in terms of this language, well, our theorem can be rephrased as saying there are infinitely many integer homology spheres with Dane surgery number greater than 1. And so, well, a natural question to ask is, well, are there integer homology spheres with maybe surgery number greater than 2? Or maybe Dane surgery number greater than 2? Great. And so this question is open, but if you've seen Ty and I working furiously in the top floor of Fold, we're hoping to answer this question in the affirmative. So, we're hoping to say that there are integer homology spheres, but you need more than 2 components in order to write them as surgery. So I'll stop there.